So if you have spent some time thinking about the question from the last video in about whether or not matrices commute, and you just can't figure it out, here's a video to explain what happens and why. So in general, AB and BA are not equal. Sometimes they're not even both defined, but sometimes they can be. And so we're actually going to start with the case of that when they're the same size. So we can obviously come up with arbitrary examples. For example, if A is a 1-by-1 matrix and B is a 1-by-1 matrix, say just 5. When we multiply A times B, it's the 1-by-1 matrix 5. Actually, that's kind of a boring example. So instead of this being 1, let's make it 2. That'll make it interesting. 2 and 5 are interesting numbers. So 2 times 5 is 10. And BA is also going to be 10. These are both 1-by-1 matrices. Their only entry is 1. This is true. It is actual math, but it's not interesting. In fact, it's no different than if we just had 2 times 5. That is precisely what we're doing when we have a 1-by-1 matrix. We're just writing some brackets in. So it's true, but not interesting. If we think of bigger matrices, like a 2-by-2, if all of our one matrix is 0, so a 0 matrix, and our other one has any numbers, so just 1, 2, 3, 4, for example, A times B is going to be 0, another 0 matrix, and B times A is also a 0 matrix. Because anything times 0 and then add it all together is still 0. The order doesn't matter if everything turns out to be 0. This is another boring, uninteresting example because you can't do a lot with zeros. Once you got them, you're stuck with them and it's like whatever. The question of matrices that are not 0, so not 0, and they commute, is such an important topic that, in fact, it becomes its own field within linear algebra. And, well, you can certainly mean a field in a more general sense. It also can be a field in the mathematical sense, where a field describes a certain set of objects that have the same property. So I'm not going to give you an example of a non-zero matrix that commutes because I can't really think of an interesting example because I'm not an expert in linear algebra at the level to which those who study this subfield within linear algebra are. For different sizes, we can think of some simple examples. So let's just say we have 1, 2. So this is a 1-by-2 matrix. And B is 2 1, or excuse me, they need to be a different size. B is a column, so 1, 2. So this is a 2 by 1 matrix. If we multiply these, A times B, we would have 1, 2, 1, 2. And so 1 times 1 is 1, 2 times 2 is 2. We get the matrix product 5. If we change these, then we would have 1, 2 along the right, 1, 2. I'm writing it incorrectly. This is the row now, 1, 2. And then 1 times 1, 1 times 2, 2 times 1, 2 times 2. So even though it is sometimes true for the same size, no matter the matrix we pick, it is always going to be different if the matrices are different sizes. And so part of that sometimes requires, at minimum, that they're the same size. Linear algebra can be incredibly rich and fascinating, and it does so many tremendous things in so many different fields that if you have the opportunity to take a linear algebra class in college, I would strongly recommend it. It can be difficult. All college classes can be. But if the idea intrigues you and you enjoy math, absolutely go for it.